we'll start with Ray Najjar.
All right, great. We're good to go. All right. It's good to be here. Good morning, everyone. It's great to be back at OCB. I almost walked up to Clark this morning because I wasn't here last year. I was thinking that's such a nice walk from the village up to the Quissit campus there. And fortunately, I was with Dennis Hansel yesterday, and he told me, oh, it's at Redfield. So anyhow, it's good to be here, and I'm really, thanks Chris and Maria and Alec and Kevin for inviting me to give a talk about some NASA-funded work about carbon budget. This is a project called wetland estuary transports and carbon budgets. Sounds like a weird diet, wet carb, like wet noodles or something, but that's what we came up with. I actually liked CATS. We had carbon accounting and tidal systems. That was kind of catchy, but that's going to be the next project, I guess. So yes, this is about the carbon budget for the contiguous U.S., and this is just the East Coast piece, which is the most finished part that I'm going to be presenting today, and involves a lot of people, and I'll sort of name them along the way. It's really, what I'm presenting today actually doesn't have very much remote sensing in it, even though it's a NASA-funded project. But we're doing remote sensing, and we're trying to get that into the carbon budgeting and accounting. So I'll show a little bit of that. Let's see. Okay, so Chris gave a nice introduction about why tidal wetlands, and I'm going to be talking about tidal wetlands and estuaries. And he talked a little bit about that too, about why they're important globally in the carbon budget. Tidal wetlands and estuaries, in my view, really need to be talked about together because there's so much, twice a day in most places. You're exchanging a lot of material, a lot of water between these systems. So they're really, one is influencing the other. I honestly, I've been sort of working my way inland throughout my career. I started out in the open ocean, and I've been doing coastal work and then estuarine work. And I came to realize, which may seem obvious to a lot of people, that tidal wetlands, at least in certain places, really contribute quite a bit to what's going on in the open waters of the estuary. And they're, these are messy systems. They're difficult systems. They're sort of, they kind of fall between the cracks, right? They're not, open water. They're not really land. They're difficult and heterogeneous and constantly evolving systems, especially with climate change and rising sea level. So I came to realize that these systems need to be studied together. And the carbon budget is sort of the balance has been my approach and take on the system. And I'm interested in the carbon budget because looking at carbon budget is a way to understand a slew of coastal issues, and especially through carbon, which acts as kind of, I think Paula Kolbe first said this, it's sort of a common currency for studying a whole slew of problems like hypoxia, like acidification, like blue carbon and carbon sequestration. I mean, if you want to study hypoxia, you really have to know how much organic carbon is being respired, right? That's a carbon budget issue. If you want to study acidification in coastal systems, you need to know how much inorganic CO2 is being introduced to the system from rivers, from exchange with the atmosphere, from respiration. So carbon really is a thing, is a currency that kind of ties things together. It's I don't know, maybe it's not the best analogy, but it's kind of like you want to understand a society or a country, looking at it through money, how money moves around is not certainly a complete way of studying a system, but knowing country's GDP, for example, tells you a lot. Or it's an important piece of information. So that's sort of the. This thing's not ticking away, so I guess I still have 30 minutes to go, or is it moving? I can't tell. Yes, yeah, I don't think it's moving. So I guess I don't know where I'm at. You can set it at. This is like at the okay, right? Okay, yeah, I could have. Right. So that's the sort of justification, is the motivation for looking at carbon budget. And actually, we don't know the carbon budget, even though you look at the Bauer et al. Paper, which is a great paper, and it's a very synthetic paper trying to get a big picture about what's going on in terms of coastal carbon fluxes. And there's a nice paper by Renier as well that sort of looked at carbon budget. But remarkably, the wetland part of those papers, the wetland area, I mean, this is a crazy thing. The wetland area used in that, in those studies comes from a Woodwell paper in the 70s, where he estimated the tidal wetland area by taking the tidal wetland area in the US, which was reasonably well known at the time, and then just multiplying, and then taking the coastline of the US, the length of the coastline, and then you divide those two, multiply by the global coastline to get the tidal wetland area for the globe. So, I mean, that's how sort of little we know about tidal wetlands globally, is that we're working on a number from the 70s based on, really just the tidal wetlands in the United States. So, so in this project, we're kind of zooming into the U.S. and trying to figure out the carbon budget for tidal wetlands and estuaries in the contiguous U.S. So let me move on. This is how I view the system, okay, by these series of boxes. And we got tidal wetlands on the left, estuaries in the middle, and then we have shelf waters on the right. And I'm really, we're interested in this as well. And Margie Friedrichs is here and has helped us a lot with the shelf water budget. Here I'm just going to focus on tidal wetlands and estuaries. And you can see the major exchanges that are going on. You have exchange with the atmosphere, and of course this happens in two directions, but the sign, at least in my convention here, is positive. It's being taken, carbon's being taken up. We have burial in all these systems, and then we have rivers providing carbon really directly to estuaries, but then tidal wetlands also provide carbon to estuaries. But tidal wetlands also fringe, fairly open waters. So there's exchange directly between tidal wetlands and shelf waters. And so those are the lateral, those are the main exchanges between the reservoirs. And then, of course, there's internal cycling. You have net primary production and heterotrophic respiration within each one. So this is what we're trying to get at for the East Coast, try to figure out what these numbers are. And this is really like a synthesis of syntheses to get at this. And so that's the main objective. And there's a lot of research questions we could, if you get a budget can answer a lot of research questions for you. And I'm just listing a couple of them here. And this is pretty basic stuff. Just, well, geez, how much carbon is fixed in the region, right? How much is fixed by tidal wetlands versus estuaries? That's something we actually just don't know. It seems like a first order thing. What's the metabolic poise? Is it the system, is it net heterotrophic, net autotrophic? Tidal wetlands I think are generally viewed as net autotrophic. Estuaries viewed typically as net heterotrophic. What's the bottom line when you add them up together? And in terms of climate impacts and carbon sequestration and then blue carbon, is the region, these tidal wetlands and estuaries, do they take up CO2 in the net or emit CO2? They bury, how much carbon is buried? Really basic questions. These are the sort of things we try to get at. And these are the methods. There's a lot of historic data compilation, just taking things from, syntheses that have already been done for one aspect of the budget, and then, putting that together in this puzzle. And this is some work that's come out of my group. We've used some semi-empirical models to allow us to extrapolate instead of just averaging data, which we do a lot of these things, we just sort of average the available data. But we've come up with some semi-empirical models, particularly for net ecosystem production and burial and estuaries. Numerical modeling has contributed to this, and this mass balance approach is what we've used as well to get at fluxes that we don't have enough information on. So if we assume steady state, now it's strictly the system's not at steady state, but maybe it's at a quasi-steady state overall, we can use mass balance to derive some fluxes by difference. So here's an example of how we use a mass balance approach in tidal wetlands. So some of the things we have measurements for are net primary production, we have measurements for burial, we have some measurements, so they're quite limited for lateral export. If we write a total organic carbon equation here, it's got 4 terms in it. 3 of them we have measurements of, and this box thing we can get at by difference. Can someone get me some water? I mean, it's like I have severe dry mouth now. I mean, I'm very nervous, actually. It's like I'm 54 years old. I'm still nervous when I give a talk. Yeah. Okay. Thank you. All right. My hands are sweaty. I'm not the best. Okay. So for DIC. For DIC, it's a similar thing. We could write an inorganic carbon budget equation, and we have estimates of DIC exported from this, heterotrophic respiration, and then we could back out the degassing flux. And then similarly, from the total carbon budget equation, we can sort of get the net uptake. So that's the sort of mass steady state mass balance approach we use. This is the system we're studying. We're building on this NOAA National Eutrophication Assessment here, and but we also add in the St. John River estuary for the Gulf of Maine. So it's really eastern U.S., not so much eastern North America, but we do include some of Canada there as well. And so we have these 3 systems. We have the South Atlantic Bight here, which has got a lot of wetlands. The Mid-Atlantic Bight, thank you, and the Gulf of Maine. The estuaries are highlighted here. The estuarine area is almost 4 times the tidal wetland area here, and this is just a breakout of the wetland area. Most of it, 60%, is in the South Atlantic. But I mean, this is globally like a very significant region. I came to appreciate that. It's a very unique system, just loaded with wetlands. So that's our system. And these wetland areas, by the way, came from Audra Hinson, who's a graduate student at Texas A&M, graduate student of Rusty Fagan, who's involved with the wet carb project. Okay, so let's get on to the synthesis. So for the net primary production, we use this nice synthesis, which is quite old now, from Irv Mendelson, showing these are harvest and clip mostly estimates of net primary production. You can see it's pretty evenly distributed. So I'm going to show a lot of these: Gulf of Maine, Mid-Atlantic Bight, South Atlantic Bight, kind of evenly distributed on a per unit area basis. That's what all these bar charts are, per unit area basis. I'm showing the standard error here, standard error of the mean here. And this is quite a lot of measurements, and you can see half, maybe more, of the net primary production is below ground. Okay, so that's one synthesis. Here's another from a recent paper by Ouyang and Lee of tidal wetland burial. Somewhat less measurements here, particularly in the South Atlantic Bight, but it looks like there's a declining trend, less burial as you go towards the south here. And these is now we're going to much smaller measurements. This is work by Maria, by the three of the session chairs here, synthesis put together by them, showing the lateral flux. And we really don't have enough. By the way, these are all East Coast measurements, so we're not looking, taking measurements from other systems. And you can see there's probably about the same, but there's very few DIC estimates, but as far as we can tell right now, about the same amount of lateral export in terms of organic carbon versus inorganic carbon. Okay, so now we have enough now to make a first order picture of what the carbon budget is. We've multiplied by area now to get things in teragrams of carbon per year. So there's about 15 teragrams of carbon of net primary production, about 1 teragram of burial, and then about maybe 4.5 teragrams of lateral export from the estuary. So then we could use our mass balance approach to get these other terms here. The heterotrophic respiration is about 12 in these units, the degassing is about 10, and then the net uptake is about 5 teragrams of carbon, okay? So that's the tidal wetland budget. So now we'll move on to the estuaries, and this is where we've used some modeling and from our good friends at the U.S. Geological Survey. This is Richard Alexander, who's developed this model called SPARROW. I forget what it stands for, but statistical, I'm sorry, I don't remember. But it's a fusion of data, direct measurements of TOC concentration in rivers, and then it combines it with the characteristics of the climate and the landscape and, of course, of the hydrology to get at this really amazing product for the whole U.S., including fluxes of total organic carbon to the ocean. Okay, so that's how we've handled the TOC. There's not a SPARROW for DIC, but we have this fine model developed, the dynamic land ecosystem model developed by Han-Chin Tian of Auburn University, which is a mechanistic, ecological, biogeochemical land model, and does a very nice job simulating the DIC export to the ocean. And he's got a number of papers about DLEM and a couple just about the East Coast. And then for net ecosystem production, this is work out of my own group. This is a research associate in my group, Maria Herman, who wrote this paper a couple of years ago about the organic carbon budget for estuaries of the eastern U.S. And this is work building on Mike Kemp's synthesis and Jeremy Testa's synthesis from Horn Point Lab, showing that net ecosystem production in estuaries, this is a bunch of estuaries all on the East Coast, can be predicted reasonably well if you know the riverine input of inorganic nitrogen to total organic carbon. Okay, and this sort of makes sense. You know, the more inorganic nitrogen you have, rather, the more autotrophic your system is going to be, positive NEP. The more organic carbon you have, then the more heterotrophic system is going to be. This is the riverine input. And these are things that we can get from models like SPARROW. So this is great. This is the statistical model approach where we can estimate the NEP for every one of those 50 or so estuaries along the East Coast. And then there's a similar approach also. This was Mike Kemp's insight based on earlier work by Scott Nixon, showing that the buried fraction of the total nitrogen input by rivers to an estuary, that buried fraction actually goes as the residence time. Tau is the water residence time in an estuary, which is something that we can calculate for most estuaries. If you know the salinity of the estuary, you know the stream flow into the estuary, you can calculate the residence time. So the longer residence time estuaries have a greater fraction of the nitrogen input buried, and then we use the C to N ratio to get the carbon loss. So now we have you know, empirical model-based estimate of organic carbon burial. And then we have measurements of the estuarine outgassing, and this is a synthesis by mostly by Govan Laruelle, who's used a lot of Wei-Jun Kai's data and a lot of data from Joe Salisbury's group and others. And you can see, you know, we're really starting to push the envelope here, you know, with only 2 measurements in the Mid-Atlantic Bight. So it's getting kind of sketchy at this point, admittedly. But you know, you go to war with the army that you have, right? And so it does look like there's, you know, from this limited amount of data, that there's more outgassing as you go further south. Okay, and then I think this is the last bit. There's a really nice paper by Jim Klern. And we also used data from a synthesis by Richard Dame for estuarine net primary production. And yeah, you don't like to see these single-digit numbers here, but that's what we have. There's probably more information out there, and we're trying to pull together as much as we can. But it looks like you really can't tell the difference between the different subbasins in terms of their net primary production. Okay, so now we can go and make the budget for the estuaries, and this is how it looks. We have about, I mean, this is one of the questions I had, is how much carbon that comes into estuaries comes from wetlands versus rivers, okay? So now we have, you know, admittedly, there's not a lot of data going into this, especially for the DIC, but now we have kind of a rough idea that it's about half the wetland input is about half the riverine input. And, you know, it varies from place to place. So in the South Atlantic Bight, that fraction will go up. There's more wetlands there, basically. Okay, so you have maybe order 10 or so, maybe more teragrams of carbon coming into the estuary from rivers and tidal wetlands. About 4 leave as outgassing. Very little turns out to be buried. So now we can use our mass balance approach figure out how much heterotrophic respiration there is. That's just the difference between these two numbers. So estuaries are net heterotrophic, and there's quite a bit that actually that goes through here. So you know, a lot of the carbon, not all of it certainly, but a lot of the carbon that comes in from rivers and estuaries kind of passes through and goes out to the shelf. A little bit gets buried, and a fair bit gets outgassed. Okay, and so now we can put together the whole sort of a regional budget, tidal wetlands and estuaries, and this is how it looks. These are some of those numbers I was highlighting before, about 7 coming in from rivers, estuaries, half of that from tidal wetlands. You look at, so I've added in some open waters here. I haven't, rather shelf waters, I haven't had a chance to talk about that, just not enough time. But we've taken similar approaches to getting burial out here, and Margie's helped us with some of the transports, and this is actually satellite-based algorithm from Sergio Signorini's work, showing that there's uptake of CO2. So that's the whole thing in terms of the lateral transports. So going back to some of our questions, questions, how much carbon is fixed in the region? Well, about 25 teragrams of carbon, and actually there's more, even though the tidal wetlands have less, like a quarter of the area, more of it is in tidal wetlands, just because the per unit area productivity is so high. What's the metabolic poise of the region? Well, it's slightly net autotrophic, right? The tidal wetlands are more autotrophic than the estuaries are heterotrophic. How much carbon does the region vary? About a teragram and a half. And is the region a source of sink or atmospheric CO2? It's almost like a wash. Tidal wetlands take up CO2, estuaries outgas about the same amount of CO2. So some of the remote sensing, I just wanted to give a sense of some of the remote sensing that we're doing in this project. We've evaluated the Mod 17. It's really for terrestrial systems, for forests and whatnot. We've evaluated it for mangrove systems in the Everglades. These are data from Jordan Barr and Jose Fuentes and others. That's in red. And the MODIS, just kind of off the shelf, Mod 17 actually does quite well. We were really surprised at how well this thing performed. It was not at all designed for mangroves. We're looking at it for marshes as well, and it's not nearly as good. And then this is some work out of Maria Georgiou's group. Her postdoc Foncao is retrieving DOC concentrations. It's very difficult in these turbid waters, but with these DOC estimates, we hope to be able to more directly estimate the lateral exchange with the open ocean instead of getting it by difference. Is what we've been doing until this point. So that's a summary. I'll put the summary back here, and I'll take any questions that you have.